Imagine a world where software components scattered across a network can seamlessly interact and collaborate. That's the power of remote method invocation, or RMI, a core technology in Java that enables this distributed computing paradigm. RMI lets Java objects on different Java virtual machines, possibly on different physical machines, communicate and share resources. In essence, RMI allows an object residing in one JVM to invoke methods on an object residing in a different JVM, as if they were both present in the same local memory space. This ability to distribute functionality across a network unlocks a world of possibilities for building robust, scalable, and distributed applications. RMI simplifies the complex process of distributed computing by abstracting away the underlying network communication details. Java developers can leverage their existing Java programming skills and knowledge of object-oriented principles to build distributed applications without delving into the intricacies of low-level networking protocols. Why is distributed computing so powerful? Imagine you are building a large-scale application like an online banking system. Handling millions of users and transactions on a single server can quickly become a bottleneck. This is where distributed computing shines. With RMI, you can distribute the workload across multiple servers. Each server can specialize in specific tasks such as handling user authentication, processing transactions, or managing account information. This distribution of responsibilities not only improves performance, but also enhances scalability. As the demand grows, you can simply add more servers to the network, seamlessly scaling your application's capacity. Moreover, distributed computing improves fault tolerance. If one server crashes, other servers can continue operating, ensuring uninterrupted service availability. To understand how RMI helps computers talk to each other, we need to look at its design. RMI uses a client-server model. The client starts the process by calling a method. The server has the object with the method. But direct communication is not easy. The client and server are in different places. This is where stubs and skeletons help. They act as proxies to help the client and server talk. When the client calls a method, it talks to a local stub object. The stub stands in for the remote object. It changes the method arguments into a format for the network. Actual remote object. Once the remote object receives the method invocation, it executes the requested method using the provided arguments. The return value or any exceptions thrown are then passed back to the skeleton, which in turn serializes the response and sends it back to the client-side stub. Finally, the stub deserializes the response and delivers it to the client, completing the remote method invocation. Section 5, RMI Registry, the matchmaker. But how do clients discover and connect to remote objects in the first place? This is where the RMI Registry comes into play. The RMI Registry acts as a directory service, allowing servers to register their remote objects and clients to look them up. When a server creates a remote object, it can bind it to a name in the RMI Registry. This name acts as a unique identifier for the remote object, allowing clients to locate it. Clients can then query the RMI registry using this name to obtain a reference to the remote object's stub. Once the client has a reference to the stub, it can interact with the remote object as if it were a local object. The RMI registry plays a crucial role in facilitating the discovery and connection between clients and servers in an RMI system. Section 6, Security Considerations in RMI. While RMI offers a powerful mechanism for distributed computing, it's crucial to be mindful of the security implications. Since RMI involves communication over a network, it's susceptible to various security threats, including unauthorized access, data breaches, and code injection attacks. To mitigate these risks, RMI provides several security mechanisms such as authentication and authorization. Authentication verifies the identity of the communicating parties. ensuring that only legitimate clients and servers can interact. Authorization, on the other hand, controls access to specific resources or methods, preventing unauthorized operations. RMI allows developers to implement custom security policies to enforce fine-grained access control. Additionally, using secure communication protocols like SSL/TLS can encrypt the data transmitted between the client and server, protecting it from eavesdropping and tampering. Section 7. Best practices for secure RMI. When developing RMI applications, it's essential to follow security best practices to minimize vulnerabilities. First, the principle of least privilege. Grant only the necessary permissions to clients, limiting their access to sensitive resources and operations. Next, input validation. Always validate and sanitize data received from clients to prevent injection attacks, such as SQL injection or cross-site scripting. Then, secure communication. Use SSL/TLS to encrypt communication channels between clients and servers, protecting sensitive data during transmission. Finally, authentication and authorization. Implement robust mechanisms to verify the identity of clients and control their access to resources based on their roles and permissions. By adhering to these best practices, developers can create secure RMI applications that safeguard sensitive data and protect against malicious attacks. Section 8. Advantages and disadvantages of RMI. RMI offers several advantages for building distributed applications. Advantages: object-oriented, leverages object-oriented principles, making it easier for Java developers to build and maintain distributed systems. Platform independence allows communication between JVMs on different platforms, promoting code reusability and interoperability. Distributed garbage collection provides automatic garbage collection for remote objects, simplifying memory management in distributed environments. Disadvantages: Java-specific, limited to communication between Java applications, hindering interoperability with systems written in other languages. Performance overhead: serialization and network communication introduce some performance overhead compared to local method calls. Security concerns requires careful consideration of security aspects to prevent unauthorized access and data breaches. Section 9. RMI use cases. Real-world applications. RMI finds applications in various domains where distributed computing is essential. Online gaming facilitates communication between game clients and servers, enabling multiplayer gaming experiences. Financial applications supports distributed transaction processing, enabling banks and financial institutions to handle large volumes of transactions securely. Network management systems enables remote monitoring and management of network devices and systems. Distributed databases allows clients to access and manipulate data stored in distributed databases. Remote Procedure Call (RPC) systems provides a mechanism for implementing RPC, enabling communication between software components across a network. These are just a few examples of how RMI is leveraged to build powerful, scalable, and distributed applications in various industries.